I'm Ethan Kwan, and today I'm going to be showing you about Boolean operations. So what are Boolean operations? Well, there are 7 of them. There is the and, not, nor, Xor, Nand, and Xnor. And by the end of this video, I promise that you will understand what each of these are, okay? Okay, but let's start with a simple concept, numbers. So most of our lives, we are familiar with 10 numbers. We are introduced to by our teachers and school and stuff 10 numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now later on, you know that you hear that, or you learn that 10 is not an actual number that you use to write with. You only use 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. So you can cross out 10, but you are introduced to a new number called 0. And then later you learn that there are other numbers below 0 called negative numbers, and they have a little minus sign behind them. Now, this is your system that you are most familiar with. But did you know there's such a thing as base 12? Yes, there is such a thing as base 12. There are 12 numbers instead of 10. I guess what we use normally we could call base 10. Or, decimal, yes. Decimal. But did you know there's such a thing as 12 numbers? Yes, because, well, you can get a base 12, which has 12 numbers. 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and to fill in for the other spaces, they use A and B. Base 8, there's such a thing as base 8 as well. It has 8 numbers. So, 0, 1, 2, 3, 4, 5, 6, and 7, right? Okay. Now, there is such a thing as binary. Binary is base 2, and if you can guess, base 2 has 2 numbers in it, 0 and 1. Now, this is pretty simple, and this is basically saying what? True or false? True or false? Is it true or is it false? Is it on or is it off? Is it high power or is it low power? Is it 0 or 1? Today we are going to be looking at binary and how to add in binary. We'll also be exploring the concept of logic gates, a type of operation that is completely different than addition and subtraction. Finally, we will be looking at how these logic gates work. So let's go. So we know that binary has 2 numbers, 0 and 1, right? So we're going to be using this binary weird system, I guess, so to calculate what 5 plus 3 is. Now, of course, we all know what 5 plus 3 is. We learned in elementary school that is 9. No, just kidding. That's 8. But this time we're going to calculate in binary. Now, this is not something you're familiar with. You have to completely change your understanding of numbers. So let's look at a number. Let's look at a base 10 number, or a decimal number. Let's call it 674, and that's the name of 674 anyway. So we know that this isn't just 6 plus 7 plus 4. That would be totally different, right? So what is this? Well, this is 600, 7 tens, and 4 ones. So we can even write this out: ones, tens, and hundreds, right? So this is calculating 6 times 100 plus 7 times 10 plus 4 times 1, which is equal to 674, right? Okay, we can do the same thing with binary, but since we don't have 10 numbers, we only have 2, we have to use a base 2 system, which is basically 0 and 1, right? So we have to count in 2s, or we have to count in powers of 2. So 1s, 2s, 8s, and 4s, right? So all these numbers. And let's say we get an example number. Let's say we get the number 1110. How does this work? How can we compute this as a decimal number if we want to convert this to decimal? Well, what we're going to do is we are going to look at the 8's position. Is there a 1 there or is a 0 there? If there's a 1 there, that means there's an 8 in the number. Plus blah blah blah. If there's a 4, there's a 1 under the 4, there's a 4 in the number. If there's a 1 under the 2, there's a 2 in the number. If there's a 1 under the 1, I guess, there's a 1 in the number. So you have to add all those up. So in this case, we have 1, 8 plus 1, 4 plus 1, 2 plus 0 times 1, which is a 0. So you're left with 14, right? Yeah. Okay, you can calculate that out for yourselves. Okay, anyway, so let's get back to the point. We want to calculate what 5 plus 3 is, right, in binary. So let's convert both of those to binary. 5 is equal to 1, 0, 1, and 3 is equal to 0, 1, 1. Now we can get rid of the 0 and the 3, but it might be helpful. Okay, so now we have this addition. So what we're going to do is we're going to start at the very right. Now what's 1 plus 1? Well, we all know what that is. That's 2. Even in binary, that's allowed. Okay? But at the start only. Again, 2 is not a number. N-O-N. N-A-N, sorry. Not a number. So we can't write 2. Instead, we write 1, 0, which is basically binary representation for 2. Right? 1, 0. Now we carry the 1, just like in normal addition. You carry the 1. Okay? And then let's do the next row. 1 plus 1 plus 0, so the carried 1 plus 0 plus 1 is equal to 2, again. But that's not allowed, so we're going to convert it to a 1, 0, okay? And then we're going to carry the 1 again, okay? So now we have a 1 plus the carried 1 plus 1 plus 0, which is again 2. But 2 is not allowed, so we're going to get a 1, 0 result. Now instead of carrying it this time, we're just going to leave it there, because there's no other numbers to add. Okay, so what's 1, 0, 0, 0 in binary? Well, 1, 0, 0, 0 equals 8. Now, we just went through all that trouble to calculate what 5 plus 3 equals 8. We just proved that 5 plus 3 equals 8 out of all that hassle. Now, that's how computers calculate things. We just thought like a computer just now. Okay. Let's try and calculate something more complicated. What's 216t plus 18? Well, here's the binary numbers. 260 is equal to 1, 0, 0, 0, 0, 0, 1, 0, 0, and 18 is equal to 1, 0, 0, 1, 0. I'm tired of saying 1, 0 all the time. I just said it again. Okay, so here's our addition. Most of them are just zeros and ones, so you can just add them up perfectly, and you'll get this number, 1, 0, 0, 0, 1, 0, 1, 1, 0. So what is 1, 0, 0, 0, 1, 0, 1, 1, 0 equal to? That's a lot of zeros. Well, you'll find out that 1, 0, 0, 0, 1, 0, 1, 1, 0 equals 278. Which is the number we wanted. Remember, we were adding 216 plus 6t plus 18. What is that? 278, right? So we just proved that 260 plus 18 is equal to 278 in binary. Or in binary 1, 0, 0, 1, 0, 1, 1, 0, and whatever else. Okay. So logic gates are basically exactly the same as these. So they're called gates because they literally allow these numbers through, but changing them. So what is the most common logic gates? Well, there are 3 of them. There's the AND gate, there is the OR gate, and there is the NOT gate. Okay? So what does each of these do? What do each of these do? So let's look at the AND gate first. The AND gate basically says if I get 2 ones, I'm going to output a 1. Otherwise, I'm going to output a 0. Okay? And you might notice the word AND in there, so that makes sense a lot. Okay, the OR gate basically says if my result has either a 1 in the first place or the 1 in the second place, I'm going to output a 1. If there's a 1 in the 2 numbers, I'm going to output a 1. Otherwise, I'm not. So if you get 0, 0, I'm going to output a 0. The NOT gate is the simplest of all. The NOT gate basically says if I get a 0, I'm going to turn it into a 1. If I get a 1, I'm going to turn it into a 0. Okay? So that's the simplest of all operations, okay? So we can make a handy little table about things, and we'll look like this. You can pause the video and examine my work. The OR one would look like this because, well, look, so input 1 is the first number, input 2 is the second number, and output is what you get out. So 0, 0 equals 0, 0, 1 equals 0, 1, 0 equals 0, but 1, 1 equals 1 because it has both 1s in it, so it's satisfied. Okay, so I'm going to say that 0 as an output is this not happy, and 1 as an output is happy, okay? That's pretty easy. Okay, so the OR gate likes to have a 1 in the number, so it'll look something like this. The NOT gate is the simplest of all. If it's a 0, it'll turn into a 1. If it's a 1, it'll turn into a 0, okay? So, that is the most common gates, right? So there's the AND, OR, NOT. Now, we are going to use those for other gates. There are 4 more gates called the XOR, NAND, XNOR, and NOR. You don't have to memorize all these names. That would be hard. Okay, and all their tables. Anyway, so let's start with the XOR gate. There are 4 more. So let's start with the XOR gate. The XOR gate likes it when it has just 1, 1, and 1, 0. So if you notice, there isn't the OR gate in there. But there's one of them that's canceled out. That's why it's called an XOR, or exclusive OR. So it basically turns every 2 pairs of numbers, so 0, 0 or 1, 1, into a 0. So the 0, 0 already outputs a 0, but the 1, 1 turns into a 0, not a 1. So that's basically how it works. The NAND gate likes it when there are zeros in it. So basically it's the opposite of the AND gate. So NAND means not AND. So literally it takes the outputs and then nots it, or I guess reverses it. So a 0 gets turned into a 1 gets turned into a 0. So the next, I guess you can call this one the Xnor Gate because literally it's so the okay, so because the XOR gate looks like this. So it's literally the opposite, right? Okay. So then there's of course the NOR gate. The NOR gate is another one, simpler one. So it looks like this. So this is the NOR table, and the tiny one in the bottom, which is really cute, is the OR gate. So if you can see the similarity, all the zeros got turned into 1s, and all the 1s got turned into 0s. So those are the 7 gates: AND, OR, NOT, XOR, NAND, XNOR, and NOR. Okay, so oh yeah, there's one more. There is the Xnor gate. I didn't explain this one yet. So the Xnor gate looks like this. It looks like this. So it likes it when it's doubled, which you might see a similarity with the XOR gate. So it's the NOT of the XOR gate. Okay? So it looks like this. See the similarity? It's just reversed, like that. As simple as that. Okay, so basically all you have to memorize, if you want to memorize all of them, is the 3 gates that are AND, OR, and NOT. Those are all you have to memorize. So the NOT, if you see an N in the front somewhere, you'll see it'll basically means AND. Not, sorry. So not, so it'll reverse it. So yeah. And then the X, if you get an X, it basically means exclusive. So the last value is switch, or so basically reverses it. So make it not the last value. So 1, 1, if it's an AND gate, it'll turn into 0, and so that would be an X AND, yes. So that'd just be a 0, 0, 0, 0, all of them would be 0, so X AND isn't really a gate, but I guess you can call it a gate. It's not really a gate, though. It's not very logical. It will just spit out a 0 no matter what. Okay, anyway. Okay, so what are logic gates useful for? Well, they can be useful for, well, probably if you have a house alarm that uses logic gates. Let's say you want to make a house alarm. Don't actually try this at home. You can try it online, like with a simulation, but don't actually try it at home. Don't try and make a logic gate like this, okay? So, just a warning. So, I don't think anyone will, though. Okay, so, let's say you want a light bulb to turn on every time somebody enters your house and the alarm is on. So, something like this, okay? So before we get started, we have to know that people write these gates differently. So here are all the different types. So the AND gate looks like half a circle, OR gate looks like half a circle. It kind of looks like a spaceship. NOT is a triangle, XOR and all those are just things, the same things up there with different attachments. So here's our light bulb, and our light bulb wants to turn on. So we want to know if the system is activated, which we're going to represent with a button, and we also want to know if there's a burglar in the house, right? If there's somebody in the house and the system is on, the alarm has to go off, right? So we need an AND gate. So let's first put the button in. The button is basically if it's on or not, and we have to connect it to an AND gate. So this is an AND gate. So we have to connect it like this with a circuit, and we have to connect it like that. And as you can see, nothing happens right now because no one's in the house. So this is going to be the front door. If the front door is open and the alarm is activated, set the alarm off, okay? So I'm going to just label this front door, okay? So that makes sense, right? So if the alarm is on and the front door is open, the alarm has to go off, right? As you can see, it's a green arrow, but for some reason the alarm is not activate. You know what? I'm gonna okay, I'm gonna switch this out for a different bulb. Let's try this one. I don't think this will work. Yes, I thought so. Okay, so let's try this one again. Let's see. Oh, there we go. Okay, so if the front door is open and the system is on, it'll alert. But if this front door is not open and the system is on, it will not alarm. Perfect. We have a logical gate. Now, of course, we want to know if anyone's entered through the back door. This only calculates the front door. So, let's look at the back door. So the back door, well, we just need an OR gate, right? So we just need an OR gate that if the front door is on or the back door is on, or both, and the alarm is on, then set the alarm off. So we're going to need an OR gate. Okay, so we're going to first label this the back door. If it's on, if it's open, it's going to be 1, and if it's closed, it's going to be off. Okay, or it's going to be closed. If it's closed, it's going to be 0, okay? So right now, both of them are closed, but it doesn't really matter what they are right now because we haven't enabled anything logical, I guess. Okay, so now we're going to put an OR gate. This is what the OR gate looks like. It's pretty cool. So we're going to connect one end there. Now, if you either set off one of them, so if you just set like this one, and that means the alarm is not on, but if you turn on, and right now it doesn't do anything, but if you turn something on and the alarm is on, then you'll get an alarm, even if the back door. But if none of them are open, well, too bad, it's not going to work. Okay, so, but, see? Okay, so, that is basically that. Doop-a-doo. Okay. Okay, so now let's just take a tour of all the gates. So let's look at the AND gate first. The AND gate, well, I'll just go through all the possible combinations here. Doop-a-doo. Here's the NOT gate, which basically reverses it. It's kind of boring, but anyway. Here's the OR gate. The OR gate turns on, if either one is on. The XOR gate only turns on if there's a 1 and there's a 0. The NAND gate turns on only if there's a 0 in the thing, right? The NOR gate, which Yeah, let's just keep playing. Okay, so the Xnor Gate is gonna be if it has 2 zeros, it's gonna be happy. If it only has 1, it's gonna be not. And Xnor basically means if it gets 2 of the same inputs, it's gonna be happy. Okay. Okay, so you can program these things to do awesome things. For example, making a half adder. Why is it not called a adder, not a half adder? Well, there is a full adder, but I'm not going to be exploring that in this video. So what does a half adder even do? Well, it takes 2 numbers and outputs 2 numbers. Now, you might think it's just the Xnor Gate or not gate, where it just takes in 1 number and outputs the reverse, but no, this is different. A half adder adds the 2 numbers together and then produces an output that is in binary, of course, but it has 2 numbers. So I'm going to be showing you how to make a half adder. And if you really want to play with this simulation that I'm using, please click the link in the description below. So we have 2 values, and we want to add them together, right? Okay, so they're not doing anything right now. So let's say we want to add 1 and 0. The output should be 1, but let's see. Okay, so we are going to add a AND gate and an XOR gate. Now, the top value has to connect to both of these, and the 0 has to connect to both of these as well. So we're going to put a 1 here, and we're also going to put it there, okay? And we're also going to put 1 here and here, okay? And looks like I got an error, so 1 sec, let me just fix this quickly. Let's see, just undo. Okay, so I think I have to make this 1 a different way, so let me try again. So let's just make a little, oops, let's just make a little path there, and then now we can connect to this one. There we go, okay. And 0, we're going to connect it to this gate here, and we're also going to connect it to the other one. Oh, cancel. It just was asking me if I want to save it or not. Okay, so 0, and now we have a half adder. Now it doesn't do anything because we didn't do the outputs. Okay, so the AND gate basically is the first number, and the XOR gate is the second number. So we have that and that. Now we have this half adder. Now which number should go in front? Well, first of all, let's test this out. So the one for the XOR should go to the back. Oops. The XOR one should go to the back, and you should have a display now, 1 and 0. So now let's add. So let's 1 plus 1 is equal to 2, or 1, 0. And we can test this out, and you can test it out too. It's really fun to play with. Of course, there are only like 4 values, but anyway. So, okay. So that is how to make a half adder. Now this is pretty cool, right? Because we wanted to make a half adder, right? So as you can see, here's our value. So 1 and 1 equals 2. Or 1 and 1. So 1 plus 1 is 2, but we can't write 2, so it's going to be 1, 0. And of course the other values work the same. So today you learned that there are 3 basic logic gates: the AND, OR, and NOT. And you learned that if there's an AND in front, it's NOT, and X means exclusive. You also learned how to add in binary, just like this. And yes, you learned how to add in binary. Thank you for watching. I hope you liked this video. If you did, please subscribe and hit that thumbs up button, which means like. Also hit that bell icon, the notification bell. Ding, 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 ding. If you like this video. Thank you for watching. I hope you liked this video. See you at howtodoflithium.com, and see you next time. Bye.